Today I'm going to talk about the method on reverse engineering flash memories. So flash memories are actually used everywhere in our daily life. Actually, the embedded devices, they have at least one flash memory there. And these days, more of NAND flashes are more used than the NOR flash. So we are going to talk about NAND flash today. And the first process of doing reverse engineering is actually desoldering the chip from the PCB board. So the method we are talking about is when you don't have access to JTAG port or other serial lines. Maybe the last option is just taking out the NAND flash itself and just take out the flash image out of it directly. So the first process is desoldering. So there is you should have a REworkstation. This one is I just bought it from Amazon. It's $50 or something. So that is the most cheap one. And maybe you can buy maybe $99 from other vendors that doesn't have. This one has multiple ones, so it supports this, hot air blower and soldering kit. So it has both of them, but if you just buy hot air blower, it's like around $90. And you apply heat around the NAND flash chip and pins. And during the time, you should put the insulating tape. Actually, I burnt a lot of PCB board without that. And sometimes there are a lot of small parts. So if you apply the heat around them, actually they are blown away. So you will never find it. It will be under some carpet maybe. So you should put the insulating tape around that. So it is really important actually. So about the temperature, the document said that 180 to 190 degrees is the temperature where the solder alloy usually melts. But I found that if you just apply like 400 degrees, I think it's just fine for most PCBs. They don't just burn down at that temperature. So you are just applying just 1 or 2 minutes heat to the NAND flash. I think 400 degrees, I think it's fine. So desoldering process is not that difficult. So it's really easy, easier than you think. And let's talk about the bit banging device, actually. So I looked up the internet a lot of times. I'm not really a hardware guy. I'm from the software reversing world, like more than 10 years. But I never tried hardware. So I looked up the internet and for information about retrieving firmware from NAND flash. And there are a lot of different methods tried by a lot of different people. And there are some myths and rumors. I tried this and it worked, but for other guys it didn't work. But using this method, using FTDI FT2232H chip, it worked fine for me actually. So this one was actually suggested from the Sprite Mode blog. And I was kind of skeptical at first time, but when I tried it, it really worked. So yeah, kind of happy at the time. So, but his method is kind of really hardcore actually. He just soldered all the chips to the board himself and put every part. But if you are from the software reverse engineering world, maybe you can just use my method. It's much, much easier. The breakup board is just sold around $20 or $30. You can just buy from eBay or other places. And this chip is really popular for hobbyists, guys who are doing Arduino or drones, because you can program other chips through this chip. So this board is really popular. So you can just buy, probably find similar one from other vendors. And actually it supports a lot of different communication protocols, and one of that is MCU host bus emulation mode. This mode actually, it doesn't emulate the MCU itself, but it only emulates the MCU host bus, the pins from MCU. The MCU we are talking is 8048 and 8051. So this is the chip MCU from Intel actually. So this one was manufactured at first like 1980s. This one is a really, really old chip, but it is still manufactured. And I found that, oh, this chip is still used in somewhere like cars. ECU is actually, a lot of ECUs are using this chip because this chip has been around like 30 years, more than 30 years. A lot of bugs are already fixed. So kind of really stable. So if some operations are really critical, sometimes they still use it. So this FTDI chip actually supports multiple commands for MCU bus emulation mode. We need the command for reading and writing through the bus, I/O bus. Here are like how many? 6 commands. 2 of them, 90 and 91, are for reading operations. So you can through 8-bit or 16-bit address. And next one, 92, 93, they are for writing through the bus, I/O bus. It can also be through 8-bit or 16-bit address space. And next one is 82, 83. Actually, they are just setting 2 bits, BD bus 6 and 7. BD bus is the name of the port from the FTDI chip. So there is a link from this document presentation. There is a FTDI note. It has more detailed explanation there. And the NAND flash itself, there are a lot of manufacturers out there, but they have a little bit different standards. But basically, these pins, out of 48 pins, these pins are supported by most of them actually. So from the right side, we can explain from the right side. There is I/O lines, I/O 0 to 1 and up to 7. There are 8 I/O lines. It means that you can do 8-bit I/O through these pins. And there is a VCC, VSS lines. They are like for power supply, 3.3 volt. And the other pins from the left side, there are some pins for controlling I/O or defining some data types. There are some pins like that. I will explain it later, actually. And here is the schematic for connecting between the FTDI chip to NAND flash itself. It's based on the schematic from sprite mode, actually. But we made some change. For example, the line between BD bus 6 to CE line, actually both of them were grounded from the initial schematic from sprite mode, but we connect them together because the CE line pin is used for actually disable the NAND flash for a while. But it is not supposed to be used that much, but some operations need to disable the NAND flash itself totally sometimes. So that's why we connected it, so we can control it from the software. And this is the actual device I made, actually. So you need wire, of course, wires and USB cable and FTDI breakout board. And the next thing is TSO48 socket. And this socket is really useful because you don't need any soldering. You can just put the NAND flash to the socket and you can connect the wires through the pins down there. Here is the pins. You can just connect it through there. So you don't need any soldering here. So I will explain the meaning of each connections here. AD bus 0 to 7, they are used for data I/O, 8-bit data I/O. So these bits can be controlled by 4 commands, 90, 91, 92, 93. They are for reading and writing byte. And for data control lines, they can be controlled through 91, 93 command. They are for reading and writing 16-bit address. That's how they are setting some flag for each data. For example, the CLE pin from NAND flash, it is actually designating a byte as a command. So if you are sending some command to the NAND flash, you just set this pin to 1, and it means, oh, I'm sending the command. So if you set ALE to 1, it means that, oh, I'm sending address. So usually what happens is that you send the command something like, oh, I need to read a page, and after that you send the address. I want to read page 00000. And after that, actually, you can read the data from the NAND flash. So the last one is WP. This pin is not usually set, but this pin is actually for something like write protection things. So if this is not set, it means that whatever you are doing, you will never, the chip will never write anything to the NAND flash itself. So you just set this to 1 whenever you are writing something to make sure that you are not writing anything accidentally. And there are other lines like IO0 and IO1 here, the first two. They are connected to CE and RB. And IO0 and 1 actually was used as interrupt handler pins in MCU, the 8051 MCU. So, for example, IO0, we connected it to CE. So it means that if we write something to IE0, set the status to 1, it will go through the NAND flash's CE line, and the state will be always 0. It will stay at 0, and it means that the chip will be disabled at that time. So if you just make it to 0 again, then the chip will be enabled again. And for IO1, so IO0 is for writing, setting the status of IO0, but IO1 is for reading. So through the IO1, because it is connected to RB line, it shows read or busy flag. So if you read IO1, you can see whether the chip is busy performing anything. So the next two one is serial data in and out. Those are called strobe lines, actually. So this concept is very general in the hardware space, actually, right? So whenever you read or write data, you are not just reading or write, you are not just doing it. Usually, you just signal the flash chip or other device, other chips before it. So using these lines, you can signal that, oh, I'm going to read some data, prepare some data for me, something like that. And for WE, I'm going to write a data right now, a byte, so prepare to receive the data. So these are called the strobe lines. And power lines, there are 4 lines. We connect 3.3 board and ground lines. We just connect them. And the good thing is that breakout board actually supports. It has port for these power lines, so it's really convenient. So for example, the read operation, if you use logic analyzer and connect it to the each lines, you can observe these logic changes. For example, the first channel 1, let's talk about channel 2 first. Channel 2 is the CLE. If it goes up, it means that I'm going to send the command. And just after that, the RB line, the channel 1 goes down, it means that, oh, it's doing something. It's kind of busy processing the command. And channel 3 goes up just after here. Channel 3, the red lines. ALE goes up, it means that, oh, I sent read command. And after that, I'm sending the address to read. And just after the channel 4 goes down and up, it means that the FDDI chip is actually reading the data from NAND flash. So we talked about the commands and the pins from FDDI, but now let's talk about the flash memory's command itself. So actually, when you control the operation from the NAND flash, there are defined commands. For example, there are read 1 and 2. They are used for reading data from the NAND flash. And read ID, if you send this command, the chip will return some ID, unique ID for the chip. In that way, you can identify the vendor and page size and all those essential information. And page program, it is used for writing data to the page. And block erase, you can erase blocks. And read status, some operations like page programs, sometimes it can fail. Then you can just retrieve the status to make sure that the previous operation didn't fail. So for read operation, so the one thing is that I'm talking about the small page and then the flash here because it is more complicated reading and writing data from small page NAND flashes. So the large page NAND flashes, which has bigger page than 512 bytes, the operations are almost same. The commands are different. You can just look up the data sheet for whatever NAND flash you have, and they have everything defined already. So, but the operation is kind of really same. So to read a page from small page NAND flash, which has 512 bytes of page size, actually you can't read the data once at one time. You read 3 times to retrieve every data from the NAND flash. So the first command is 008. It will read the first half of the data page, and 018 will retrieve the second half of the page. And finally, to retrieve the OOB area, the out of band area, you need to use 58. The reason why the NAND flash has OOB data is 16 bytes for a small page NAND flash, is that because the reason why they have OOB data is because sometimes because NAND flash is just physical device, right? So it can fail, or some pages have some bad some pages. In that case, using this OOB area, you can just mark them as bad or something like that. I will explain it later. For read operation, this is very, the table that shows each pin state when the read operation is done. So when it is reading, it will send the command 0, 01, or 58, one of 3. And at the same time, it will set CLE pin to 1 because this data is command. So CLE here value is just defining the data type here. So IO 0 to 7, 1 byte is command. So next one, it is sending like address. So at the same time, ALE is set to 1. It means that I'm sending address right now. And the RB signal goes down briefly because the NAND flash must be really busy preparing the data. And actually, data will come out just after that. But if you look at the RE and WE, for writing this command and address, the state, the signal from WE changes. It goes down and up to indicate that I'm sending command or I'm sending address. For reading data, the RE line goes down and up to indicate I'm ready to read some data from NAND flash. So if you take the logic analyzer dump from this actual read operation, it looks like this. And when it is sending the command, the WE and CLE goes CLE goes up and WE actually goes down because it's sending the command. It will make changes to the status of WE to indicate that I'm sending the command. And after that, when it is sending the ALE, same thing happens for address. And when it is actually reading data, the RE, the read data. Actually, it looks like just the phase change, but it is like reading like for example 256 bytes in this short time actually. So from the code point of view, so actually the sprite mode actually released the C++ version of code, and the other guy actually refactored the whole code and made it as an open source project. And I just converted all those codes to Python and added new features there, because Python is much easier to dealing with, right? So whatever experiment you are doing, you just change a few lines and you can experiment. But for C++, you need to understand the whole class structures. So yeah, this one I just converted it, and the basic functionalities are same, and I added more functionalities there. And this one is open source actually. So for this one, for reading, so you just need these commands to read data from a page. If you look at it, it's just sending the command read 0 and read 1 and read OOB command, and after that it's just reading the data. And talking about the reading data, for example, the first command is flash_tool.py.i. It will just show the basic information about the flash chip. And -r and file name, it will retrieve whole data from the flash memory and save the file to flash DMP file. And if you look at the how fast it is, it's 9K bytes per second. It's not that fast actually. So you need to wait like maybe 5 minutes or 10 minutes. If I actually dumped a USB stick, 2 gigabyte USB stick, it takes almost half day. So I look up a better way actually, because the -r option only reads page by page. So basically you are sending the command for each page. And I found that some memory chips, some flash chips, for example, Samsung flash chip, NAND flash, they support some additional mode. Something like, it is called, the sequential row read mode. You can read block by block. So one block is 32 pages in this case. So you can save the time for sending additional command for each pages. So you can just pass -s option here. So it will use sequential row read mode. But I'm not so sure other flash chips will support it, but basically you can look up the data sheet from those chip vendors. So with this mode, it shows 50K. It's almost 5 or 6 times improvement in performance. And about the write operation, everything is almost same except that it is sending command 80, and after that it is sending address, and after that it can just send the data directly, page data or OOB data. And the other difference is that it will send additional commands like 10H. 10H is the program command. So before you send the 10H command, even though you sent all data, nothing will be programmed to the page. It is just preparing the data. But if you send the 10H command, then it will commit whole changes to the page. And after that, it will send the 70H command. It will read the status from the last operation to see if the last write operation succeeded or not. So if IO0 is set to 1 or set to 0, it means that the last operation succeeded. So for example, the code for this operation is almost same as the other one, the read operation. The sec-in command here is 80H, and page prog is 10H, and it's programming. The one thing is that actually before sec-in, it's calling sec-in command, actually it's reading. So read 0, read 1, read OOB here, but actually they are not reading, but they are. The read command is actually has different meaning here, because the write operation can only performed in to the, what is that, half page. Not whole page can be programmed in small page NAND flashes. So each read 0 is just setting the pointer to the start of the flash memory. So after that, it is just writing. And read 1 will just set the pointer to the middle of the flash memory, and after that, it will be writing data. And read OOB will be setting the pointer to the OOB area, and it will be writing OOB data. So if you look at the logic analyzer dump, it looks like this. It's a writing command, the writing address, they are almost same. But in this case, there is no changes in RE signal. So the changes happens in WE signal because it will be writing a lot of data to the flash memory. And now we have all those, all the bare metal image we wanted. So from the hardware world, we are coming back to software world. Here, so for example, if you look at the page and OOB data, this one is 512 bytes of page data, and it has OOB area here, so 16 bytes. The OOB area has different format for different vendors, but usually they have same component there, something like ECC, 3 bytes of ECC, and 1 byte bed block indicator, and the other bytes are used for other uses. They are reserved for application use or something. So we will see how they are used here later. And for example, ECC, from here, there is a ECC 3 bytes. The first 3 bytes from OOB area is ECC. But other vendors, sometimes they place ECC here. Even Samsung, old document shows that ECC happens around here after 6 bytes. But the flash chip I worked on, it has the ECC at the start of OOB area. ECC, this concept is really interesting because the concept actually came from like 1950s. The first computers, actually they used, the punch card. So you programming means you punch the card actually. So because the human is doing it, there can be some errors. But if you make error, you should start from the beginning. It's a lot of effort. So if the error is just 1 bit or something 2-bit errors, maybe you can put some checksum that can correct it automatically. That's what Richard Hamming thought about, and he made up this ECC Hamming code concept. And the ECC is basically using the same concept, and this concept is also used in hard disk technology. So in a lot of senses, actually hard disk and then the flash, they are very, very similar. And basically, this table actually shows the concept of ECC used in NAND flash memory. So this diagram is based on the documentation from Samsung presentation I found somewhere. For example, this one has small page blocks and 512 bytes here. And each bit is represented as one blue cells here. Bit 0 to bit 7 is just 1 byte, and there are 512 bytes. And basically, we are checksumming like every rows and every columns, and with every different combinations. So it might sound really complicated, but it's really easy concept. For example, in this case, we are calculating P8 apostrophe value. Basically, you are XORing every bit from byte 0, byte 2, and byte 4, every even row, even rows, and like up to 510. So just XOR every bit, and you get P8 apostrophe value. How about P16 apostrophe value? So it will be just calculating bits, XOR bits from 0, 1, yeah, something like that, 4, 5, and skipping 2 bytes, and it continues. That's how you calculate P16 apostrophe. And other values are same concept. You calculate every parity bit, And the code is really simple here, the Python code I wrote. I think that there can be some more optimized way to write the code, but this shows the concept very well. And everything is available from the open source project I disclose. And we calculated the row parity bits, and now we need to calculate the column parity bits. And it is same concept, right? So for the P1, you calculate the bit 7 parity bits. And for example, P2, you are using bit 7, 6, and skipping 2 bits and using bit 3 and 2. And in that way, you are doing same thing for P4 and P1, P1 apostrophe everything. So you have a lot of parity bits collected now. This is the Python code. This is a really simple code. And the last step is, because you collected every parity bit for different combinations, and you just need to save it to bytes in byte form. And for these bits, you only need 3 bytes to save all those parity bits. And this is how the flash memory that I worked on actually saved the bits. The thing is that every vendor, even the different flash memory from same vendor, use different locations for each bit. So if you use this algorithm here, probably it will not work for your own flash memory, because they are using different locations for the bits. So it's kind of a guessing game. So you calculate some value, and you need to figure out which bit is going where. But it needs some time. It's doable. So for example, so you might wonder how these parity bits can detect and fix the bits. So the one good thing about ECC is that if there are one bit error, actually you can fix it. So if there is 1 bit error there, and actually you can pinpoint that location, and you can fix the bit, because there is only 2 states in bits, 0 or 1. If that bit is wrong, it means that it might be the other value, right? If that is 0 and the bit is the checksum is wrong, it means that it should be 1. So for example, if you go back here, let's think about just, for example, the bit 0 from byte 0 is wrong. So it should be 1, but it's somehow 0. It should be 1, but it's 0. And this error will make P8 apostrophe wrong, and P16 apostrophe wrong, and P32 apostrophe wrong, and so on. And it will make this error will not affect other values, but it will affect P1 apostrophe and P2 apostrophe and P4 apostrophe. So you will find which checksums are wrong, and you can pinpoint the exact location where the bit failed. So in that way, you can correct 1 bit error. So that is the ECC concept, and the bad blocks. Bad blocks can happen. So ECC is for minor errors, but if the errors are major, then you need a bad block concept. So for this case, it is using FF bytes, 6th byte of OOB area as a bad block indicator. If it is FF, it means that the whole block is fine. So actually, it is using the first page of the whole block. So if it is FF, it is fine. Well, for example, the tool that I released actually supports bad block checking here. So you run downflash pi and -b, and the image file, actually it will dump every blocks that are marked as bad. And for example, the first result here, 3A5CC00, if you go to that location, actually, if you check the OB area, actually it is set to 0. It should be FF if the block is valid. It means that the block has some physical error, so it can't be used anymore. So you can skip those blocks when you process these raw NAND flash images. So you now have some meaningful data, just removing any bad blocks, fixing any ECC errors. Now you have something more meaningful for software reverse engineer. And The thing is that I'm talking about the NAND flash is used in embedded devices. But I dumped some NAND flash images from, for example, USB thumb drive. They don't use this layout. So because they don't need any U-boot or any JFFS there, they are just using their own format, like a proprietary format. Maybe they are using some fat table. Maybe they encrypt some data. Each vendor will have different formats or whatever, so you need to figure out them. But mostly I'm talking about the NAND flash layout that are mostly used in small embedded devices like routers or POS devices and those devices. And the thing is that ARM-based, the ARM CPUs, they have some microcode actually checking every storages that are connected to the chip, the CPU. And if it finds NAND flash, it will just load the first block from that NAND flash. So the first block will contain the first stage boot code there. So it will have a lot of like ARM instructions there. And after that, we will call next level bootloader that has more complicated logic. And that is usually U-boot, and maybe there are other options too. And after that, it will have some U-boot images, multiple images. And finally, it will have a real file system like JFFS2, some incremental journaling file system there. And let's talk about each one of them. So the first stage bootloader looks like this, and they are just starting from the block 0, the first block 1, actually. So you can just take out the first block and just save it to file, and you can just load it from IDE and set the CPU to whatever CPU you use. So, for example, in this case, I set it to ARM, just ARM, and it will just disassemble like this. And it is actually ARM code there. And if you look up some addresses there, and you can search for that, and actually they represent some pins or some registers in ARM CPU. They are really low-level operations, and some strings, some interesting strings, something like that, shows that NAND bootloader Adam 3.24. I don't know if this one is open source or some commercial one. But the message is something like a loading U-boot. So you can see that this one will load U-boot after this. So you take out the U-boot code. Probably from the next block, the U-boot code will start, and you can just take dump from that part, and you can just load it from IDA, and it will have some U-boot code there. But they are not really meaningful because U-boot is just the open source code. And probably they will just use it. So there are a lot of things to look into here. But the interesting part starts here, the U-boot code. And after that, there must be 1 or 2 U-boot images. Actually, they are just packed with U-boot format, U-boot image format. Here's the header file from the U-boot project. And the first 4 bytes are magic value. So identifying the U-boot images are really, really easy because you just go to the start of each blocks, and if the first 4 bytes are this magic value, there are a lot of chances that those blocks are used by U-boot images. So in that way, you can easily identify U-boot images. And there is a tool called binwalk, actually. So I guess that one is also using some pattern matching. So probably you don't even need to use it because you can go there, check 4 bytes, and there is a header structure here. So even there is image length. So you can use this image length to find the end of this U-boot image. And here's the way how you can calculate the whole image, end of the image, because the raw image contains OOB area, so you need to calculate that part. But basically, it's just math. And after you calculate the end of the U-boot image, actually you can use dump flash tool that I'm going to release, and you can just set the range from this address to this address and dump out to this file, and from this flash dump file. And it will save, and it will remove OOB area and battle blocks, and it will save as a one file to the file system. And The good thing is that IDA supports U-boot images, so you can just load up the U-boot image, but it has some restrictions. For example, one of the format from U-boot is multi-file image, and actually IDA is not recognizing it correctly. But the other way is just opening up the image from hex editor. If this byte, the type byte is 4, it means that this one is a multi-file image. Then just 40 bytes is the U-boot image header. Just after this U-boot image header, there comes the image length for each each file. There are multiple files. In this case, there are 2 files, and after that there is a 0. It means that it's the end of the image length. And using this information, you can actually take out each images. And from the Linux, you can use the MK image, and you can see there are 2 images there. But I don't think there is any tool to actually extract each image separately. But you can just use a hex editor, or maybe you can write some Python, very basic Python script if you want. And one of these images I dumped actually was a RAM disk, and that one is compressed, and I just decompressed that image, and I found that that one using file command, and even though you just open it up from the hex editor, you can see a lot of file names there. You can guess that, oh, maybe this one is a file system, right? So this one, in this case, the machine that I worked on, the chip I worked on has ext2 file system there. So I used the MTD device to load the image. You can just use DD. This is straightforward process. You can just mount it to your system, and you can actually look into the file system. You can modify the files, and you can write it back to the flash memory if you want. And the other images, sometimes, many times they save kernel images to U-boot images. And even the MK image command can tell whether the U-boot image is ARM Linux kernel image or not. So in this case, it shows that this one is uncompressed. But actually, it has some compressed image here. So there are some debugging messages here. But basically, from the kernel image, you can just search for this gzip image magic value, like 1F8B. Probably you will just find one instance of it. And after that is actually gzip kernel image. And you just take out that part. And even the debugging messages here are kind of useful because it's just saying uncompressing Linux or other messages. So you can easily guess that this part is actually a compressed kernel image. You just take it out and you can load it from IDA. But all those things here are actually use kernel images, U-boot, and some basic RAM disk image. But the actual data is saved in JFFS2 file system in many cases. So that I know that there are multiple journaling file system, but one of those systems is very popular, like JFFS2 here. And advantage with working with NAND flash memory raw image is that actually the JFFS2 file system leaves, when you are formatting the NAND flash, it will leave some markers in the OOB area. And for example, here, the last line from the hex dump is 3 bytes are ECC, and 6th byte is a bad block indicator. And from the 6th, 7th, 9th, from the 9th byte, they are used by JFFS2. So they will use always same marker here. So I don't know how they chose those values, but they will use always same values if the block is used by JFFS2. So you can easily identify JFFS2 file systems using this method. So you can use MTD device and do same thing as you did for RAM disk. So you just take out the JFFS file system and just write it to the MTD block and just mount it from that MTD block. and you have full access to the file system in this case. So this is one thing that I improved with the open source project. Actually, the original NAND tool project didn't support writing. Actually, some code was there, but actually it was obvious that the code was never used because there is no code actually that is calling that part. So the Flash tool Python code will write data to the pages actually. So the process is simple. So you make some changes to the file system from MTD block, and you can just dump out whole image using DD. So here DDIF from the MTD block and just save it to file, and you can directly write whole files to the NAND flash. But actually the image from MTD doesn't have OOB data. You need to put the OOB data using this tool, dump flash pi, and -r will reconstruct every OOB data. Supposing this image is JFFS2, it will put every JFFS2 erase marker, and it will create a new image like mtd block 0 OOB dot dump. This is a new dump file that has OOB lines data, and you can program it using Flash tool, and you can pass W option here and pass the file, and -r and the location of the write operation, and this is the start, and because you don't know the end, you don't care about the end, you just pass 0xFF and you will write the file up to where the file ends. And that is what the software thing happens. And the thing is that the next tricky issue is that actually you need to put back the NAND flash to the board, the PCB board. So this is the most difficult part actually for software reverse engineers, because this is the SMT chips. So SMT is surface mount technology chips. They are supposed to be handled through some automation like machines. It is supposed to be put into the board through the machines. That's how they made in the first place. So just soldering SMT chips to the PCB board, it takes some effort. You need some trainings, some learning curves. And I found that there are a lot of YouTube videos about how you can put the SMT chips on the board using solder or some basic equipment you have. And there are many different methods suggested. And you might try with some chips that you don't really use, and you can try that. And if you are really good at it, maybe you can try that on some important devices. But it takes some effort. The other issue is something like it is really common that you see some bridges. And here, this is actually from what I did for my project. So damaged pins, actually the pins, like four or five pins are just gone because I applied too much heat, and I applied it repeatedly, and I applied flux again. Actually, flux is really bad for these pins because they actually melt these chips away from the board. These things really happen really commonly, but the good thing is that these damaged pins usually happens when the pin is not connected to the main circuitry. So we talked that some pins from flash memory, they are not actually doing anything. So they are just reserved pins. And on PCB board, actually the pins on the PCB board, they are not connected to anything. They are just glued to the PCB, and they are more vulnerable to this damage. So in that case, even though they are damaged, maybe you can try to connect other pins. Maybe it will work. You can just refer the data sheet from the vendor, the NAND chip vendor, and you can be sure whether that chip is used or not. And these projects are already released, and the Flash tool project, it's on GitHub, and it supports write operation, and it supports a fast sequential row read mode, which is 5 or 6 times faster than the old method. And because this code is written in the Python code, it is like almost 600 lines or something. So you can do some experiment with this Python code. There is other project, Enhanced NAND tool. So this one is from the original NAND tool project. I just added the writing support. The one problem is that this NAND tool project is using old schematic from sprite mode. And for this new Flash tool, it is using new schematic from me, which is presented here, because the fast sequential row read mode needs some control over CE pins. So the other projects like dump flash Python code, this one actually manipulates the image file in the low level. It can handle ECCs, battle blocks, but I put a few logics for ECCs, but probably your vendors might be using a little bit different ECC algorithms. In that case, maybe you can add it based upon the code already there. Probably it will not be that different. A little bit different, only the location changes. And the last tool is dump JFFS2 Python code. This one actually parses each JFFS record from the raw image, and it can tell the history of the file operations that happened in the JFFS file system. And the conclusion is that even though using JTAG is recommended doing some embedded system research, but there are some occasions that JTAG is not feasible. Maybe you don't have any time to figure out how JTAG is there. Maybe the JTAG is obfuscated a lot, or it is removed, it's just burnt out. And there can be a lot of different situations. And the other case is the USB, for example, USB thumb drives. They don't have any JTAG, obviously, because they don't have any real CPU there. They only save some data there in the flash memory. In that case, you just take out the flash memory from USB thumb drive, and you just dump out the data and look into it. It's really interesting, actually, what they are saving in raw level format. It's really interesting. In that case, you can use this method. And there are actually commercial solutions for same function. Like, I don't know exact the vendor name. They are selling like $1,000 flash reader or something, but this one is just $60, up to $60, and you can make one device. And every code is open source and it's free. And you can basically, disordering method is called destructive method, but it's not really destructive. You can just put back the chip again back to the PCB board. It's possible. But the one problem is that if hot air blowing method, it's much safer. If you use chip quake or other method, actually they make resoldering very difficult, because it leaves a lot of chemicals or whatever. It's not that easy to put back the NAND flash again if you use that. But hot air blowing, it's kind of okay. And there are many factors like ECC. You need to consider ECC, battle blocks, and JFFS2. Probably other embedded device might be using other journaling file system. You need to consider that. And you need to consider U-boot images. And there are a lot of things to consider if you use this method. But it's worth to invest your time and resource when you don't have any other options. And that's it. And there are credits for the original design for NAND reader and writer. It was sprite mode. I tried a lot of different ways, but this one is the only way that I succeeded. And NAND tool, it's the code from sprite mode, and the guy who I can't pronounce the name, he actually refactored the code, and I wrote my own project based upon this code. And that's it. And any questions? Or I think we have 5 minutes.